Hello there. Today we're going to be talking about the concept of center of mass. When Newton formulated his laws of motion, he abstracted masses into points. This simplified his analysis and enabled him to formulate his laws with the simple mathematical tools that he had at his disposal. But real objects aren't points. They are massive, their mass is distributed in space, and forces can act anywhere on these objects. And so there has to be some way to be able to integrate real bulky items with the kinds of point masses that Newton assumed in his laws of motion. Fortunately, there are some simple ways to do that, and we're going to be talking about one of these important concepts today. That concept is the center of mass, or sometimes called the center of gravity. Now, when you have an object, if you have a simple shape, say a sphere, the center of mass is quite simple. The center of mass is right in the center of the sphere, and you can easily calculate it with a mathematical formula that tells you where a point is in space with respect to the volume. But again, real objects aren't ideal spheres or cubes or rectangles or things like that. They come in complicated shapes, and so you need to have some way to be able to estimate where the center of mass of these complicated shapes is. Otherwise, you'll just be dealing with relatively boring situations like billiard balls and that sort of thing. Okay, so let's consider how to estimate the center of mass of an object with a complex shape. And so what we're going to do is we're going to make complex shapes out of index cards, and we're going to take advantage of the fact that the index card is flat and of uniform thickness. Therefore, the weight of it is going to correspond to the surface area of whatever object it is that we cut out with our scissors. All right, so let's just go over here and cut out a complicated shape, any kind of complicated shape that we would like. So let's do that. Let's make a nice curve right here. Okay, and we will continue to cut out through here. Let's put in a couple of odd curves there, for example. Let's do that. Again, we're going to make this as complicated as we like. And this object has a mass. The mass is proportional to the surface area of this times the thickness of the piece of index card. All right, now the determination of center of gravity means trying to find the point at which the mass on one side of the point is equal to the mass on the other side of the point. And there's a very simple way of doing that. What we're going to do here is we're going to take our object of complicated shape, and we're going to drive a pin through it. And we're going to use a little thing to hold the pin in place. What we want to do is we want to take a pin, put it through this loop of thread right here, and we're going to take this loop of thread. We're going to first push it through the object. We're going to take a loop of thread, push it through the hole that we just made. We're going to take the other end, which also has a loop, and we'll take a little piece of cardstock, run the loop through there, like so, and then punch our pin through there. Now what this gives us is a little sling that enables us to hang this complex object from a stand of some sort. And we're going to do that now. We're going to move this stand right over here into the field of view, and that should put us right. And we're going to take our object. We're going to bring it right over here, and we're going to hang it from this stand, just like that. Now, if you take this object right here, imagine a line that hangs down vertically from this point where it's hung. And at that line, because this sits still, this tells us that the mass on one side of the line is equal to the mass on the other. Fortunately, we have a way that we can do that. What we'll do is we will take a little clip here, and you can see that the clip is hung on by a thread, like so. And we're going to take the loop, we're going to take the clip, we're going to hang it on one side from the pin on one side. We're going to take the other loop and hang it over there. And what we have now is, everything's nice and even, what we have here is our imaginary vertical line is now indicated by the hanging vertical thread. Now we'll just make a couple of pencil marks there. One there, and there, and there, and there. Now we can take our object, take it off, bring it over here with a ruler, and now we can connect these imaginary lines with a pencil line. Now we do the same thing at another, now we can do the same thing at another point of the object. Let's do it here, for example, right there. Again, we will take our loop of thread, we'll take our loop of thread, poke it through there, and then threads are very notoriously tricky. All right, let's put that in there. We'll poke the thread through there. Now we have one loop of the thread hanging there. We'll take another little piece of paper, put our thread through there, if I can ever get it on there. Take our little sheet of paper. Again, we poke our needle through there. And cinch it down nicely. And now we have it hanging from another point. Now we will take this over to our apparatus again, hang it from the standard, make sure everything's nice and tight. And what you see here now, of course, is that the paper cutout is hanging a different way. Now we can do just what we did before. We can take a loop of thread, hang it from one point here, let's do that again. Run the loop through one end, bring the loop around to the other end. I'll get this eventually. There we are. And we'll let that now hang again. Okay, now you can see that we have another imaginary line that extends downward. Let's just mark that. Bring it over here to our sheet. Make a couple of marks. Dismantle this Rube Goldberg apparatus here. Draw another line. And this tells us what the center of mass is. We'll just circle it right there. Now, if we hold the paper this way, this means that, and if this is gravity, this means that the mass on this side is equal to the mass on this side. If we then turn this around so that gravity is now pointing down this way, this means that the mass on this side of the line is equal to the mass on this side of the line. And the point where those two different distributions of mass intersect, which is at the center of gravity, is that is the center of mass of the object. Now, the center of mass is a very, very important concept. Among other things, it says that no matter what the orientation of this mass is with respect to gravity, then the object will be stable with respect to gravity. Let's demonstrate that in a fairly simple way. What we're going to do now is we're going to punch a little hole right through there, and we're going to put an axle in, and we're going to show that no matter what the orientation is, at least we hope that's what we'll show, no matter what the orientation of the object is, we will be able to, it'll be stable. So let's take a barbecue skewer right there, punch it right through there like so. And we can take another little piece of barbecue skewer, which is right here, run it through there so it sits tightly. And now we have an object that's on an axle that can turn around. If we then take our threads, loop threads again, what we can now do is we can take our object that is on its axle, put the thread on there, I never was very good at sewing, so it's going to take a few seconds for me to do that. Okay, so there's the thread on one side of the axle. Hold it in place. Let's bring the other side around. Put that in the axle. We're getting there. Okay. There we go. There's the on the other side of the axle right there. So now we should have loops on both sides, like so. And now if we take this and we hang this up on our apparatus right here, if we're lucky, the loops will hold on both sides. And it is, let's get it oriented so it's not going to fall off. And it's stable this way. And if we turn it, it's also stable this way. Now, the concept of the center of mass is important because it enables us to follow not only objects that have complicated masses distributed about a center of mass, but it also helps us follow motions of swarms of masses as well. So for example, suppose we have a mass that has some kind of complicated shape. It has a center of gravity right there. And suppose we launch that mass with some kind of a force. So we apply an impulse force. The trajectory for the center of mass is going to follow a parabolic arc that's going to look something like that. And so sometime after we launch it, we should see the object. And again, I'm going to try to draw it as faithfully to the original as we possibly can, but obviously I'm not a very good artist. And at some point, that's going to be at that point right there. Suppose at that point, though, we have a little explosive charge in there and we break it apart, just as, say, might happen with a fireworks. What will happen then is that you will have two objects that will fly apart at different velocities. You've imparted momentum to them. So this corresponds to the top half, this corresponds to the bottom half, and each of those will follow their own trajectories. This one might follow a trajectory that looks like this one might follow a trajectory that looks like this, but there is still a center of mass of that system. The center of mass is the average between the center of mass of one fragment and the center of mass of the other fragment. And that average center of mass happens to be the center of mass of the original object. So the center of mass of the two objects, averaged together, will follow the identical trajectory that it would have if it had stayed together. It doesn't matter that you've broken it apart into two objects. The two objects have an average center of mass that follows the very same trajectory that a single object with the center of mass at that point would. Okay, well, that's all for now. In some other videos, we'll be talking about adding the complication of rotation of these masses, and we'll try and tie it into an interesting application for biology of some of our local maple trees. Well, all for now, and we'll see you another time.